is Josh. I was a computer science examiner for multiple exam boards, head of computer science in UK-based schools, and now I run a tutoring business. And all these lessons are trying to help you get better for your A-level computer science exams, and they are just round the corner. I've been trying to put out as much content as possible for you, and today's lesson is all going to be to do with different sorts and searches. And what I've tried to do is I've tried to split this up into how it works, the coding around it, and then at the end, what I'm going to do is I'm going to talk about the time complexity of these ones. It's a short amount of time until your exams. And the thing that I would recommend with trying to revise this is that sometimes people can get, and I know this might sound a little bit strange, get very hung up on the fact that they don't fully understand how it all works. Obviously, what I want you to do is I want you to fully understand how it works. But let's say that you've only got a short amount of time until your exams. I'm going to show you the definitions of what to write to get the top marks on this one. And if all you can do is you can just go over this lots and lots of times and remember the definition off by heart, that is going to be the same as if you fully understand it. Now, you could get a question where they get you to quick sort a collection of numbers. Now, in that case, yeah, you might not be able to answer the question, but if all you can do, and the thing that you've got in your power is that you just stuck there, and what I don't want is, because I'm not saying to not learn these things, I'm just saying that if you've only got a short amount of time and all you can do is learn the definitions, just do that. That's going to be better than sat there and, pulling your hair out, trying to get you to understand all of the absolute intricacies of everything. Because that's where I see some students stop, is that they get a roadblock because they're like, I can't move on until I fully understand it. Of course, if you've got lots of time, yeah, take your time with it and fully understand it. But if you've got a day or two until your exams, do what you can. Okay? So anyway, a couple of definitions that I want you to get down anyway. Abstraction and decomposition. So abstraction is all to do with ignoring unnecessary details and focusing on the important parts of a program. Decomposition is breaking a large problem down into smaller problems. Now let's have a look at quicksort. So I'm going to show you a question after I've done this. I'm going to show you a visual example as well of how it works with this one. And with a quicksort, say we've got this list here. Now, what you're going to do is the first thing is you have to select a number that is going to be what's called the pivot. Don't get hung up on the word pivot. Essentially, pivot just means a number where you're going to go through and check, and all of the numbers that are less than that number are going to go to the left-hand side of it and make a new sublist. And then all of the numbers that are larger than it are going to go to the right of it in another sublist. So people get hung up on the word pivot, but essentially pivot, all it means is we're just going to pick a number where we want to go for we want all of the numbers to go to the left hand side of it that are smaller, all the numbers that are larger than it, we need to go to the right hand side. And it doesn't generally, well actually it does matter which one you pick, but it's generally what you're going to go for is a number that's as close to the middle as possible. And I'll talk about some ways in which you can select it, but generally not a massive issue about which one that you pick, but generally as close as you can to the middle. So step one, pick a pivot, which is close to the middle, maybe we should say as well. All the numbers that are less than 56 so you go for each one, and then you create a new sublist, which is smaller. Step three, you make all of the numbers go to the right of it that are larger. Then of these sublists, you pick a new pivot, and then so I've gone for 34, and then all of the numbers that are smaller than 34 go into a new sublist, and then all of the numbers. So it's going to look like this, where you've got all of the numbers in the left hand side are 23 and 28, and then on the other side you pick another pivot. All of the numbers that are either larger or smaller, so all the numbers that are larger go to the right hand side, all of the numbers that go smaller, so 81 and 85 are both larger, so they go to the right hand side of it. And then you just keep repeating this process until picking a new pivot, a new value, which you're going to check it against, until you've got 1 or 0 items in the sublist, and then the list is sorted. So if I show you a visual representation of this, so you've got 56, and then you split them, so 23, 34, and 28 are the new sublist, and then you've got 81, 60, 66, and 85. You then pick a new pivot, so I've gone for 34, 66, and then you go for, okay, these need to, if they're smaller, they need to go to the left-hand side. Both of these two are smaller, so 23 and 28 go to that side. 81 and 85 are go to the right-hand side of 66 because they're not smaller than 66. And then we pick a new pivot, 81, and then 85 is going to go there. It's now everything's there's nothing else that we can do in this one, so that's now that part of it sorted. And as you can see, it goes 56, 66, 81 and 85, so that part's sorted, and then 88, 28 and 23, and then that is sorted. Okay, and that's just the instructions again on there. Now, as I said, people, if time is short between your exams and you're just like, that made no sense, go over it a few times. So I'll give you some strategies of trying to make sure that you understand quicksort. Go over it a few times. The one that I've done, have a look and some different examples and try it out. Picking a pivot and going, okay, is it smaller? It's going on that side. If it's bigger, going on that side. And if you still sat there and you're like, I've got a day until my exam and I just have no idea what I need to write, okay? This was a question that I went and found. And this is what you needed to write to get, so it was 5 marks, so you needed 5 bullet points. So choose a pivot, compare each element to the pivot, put the items less than the pivot in the sublist, put items to the right of the pivot in the right sublist, choose a pivot of the next sublist, and then it's talking about pointers and stuff here. But if you put all of that there and repeat the process until the items become a pivot, each item becomes a pivot, you're going to get full marks on this one. It's 5 out of 5. So if that's all you can remember, which is still tricky, you're going to be getting some marks there. And if that's all you've got time to do, don't sweat it. Move on to some of the easier stuff, which we're going to go on to. So I just wanted to sort of talk to you about that I think that's a really important skill in revision, is when you've got a limited amount of time, just do what you can. Don't worry about it. Just do what you can. Do what you can understand. The code is here for a quicksort. Now, generally for the longer ones, and this is a bit of a longer one, is I'd make a flashcard on this and practice this until I can remember it. Reason being, they generally do fill in the gap questions on these ones. So it's like they would say like, what, fill in the gaps for these two. And it's generally going to be to do with like the leftmost index and the rightmost index. Yeah. Or missing one of those. So just practice this flashcard until you can remember it off by heart. Going on to the searches now. So I think quicksort is the most challenging one to understand. So now we'll go on to some of the easier stuff. So we're going to go on to the searches. So remember, searches are generally an easier, sorry, not easier, I shouldn't say that, but they're a different kind of algorithm. And how they're different is they're looking for values. Sorting it can be sorting a list of numbers or a list of names so that we can perform a binary search on it, because a binary search is a lot quicker than a linear search. So this is the steps of so the question they may ask you is just to perform a binary search and talk through the steps. So this is what you do. Imagine you're looking for Mo. First thing we do the number of values plus 1 divided by 2, which takes us to, so there's 11 values, plus 1, 12, divided by 2 takes us to Lara. We then go, is Lara Mo? Everybody always forgets to do that check because they're like, well, I can clearly see it, but the computer doesn't know that. So it compares the values and goes, is that the one we're looking for? No. And then it goes, is Mo greater than or less than Lara in the alphabet? And then it says less than, so it discards everything less than Lara and Lara. Then goes and finds the next middle and goes, is Pam Mo? And then it goes on to and repeats that process until it finds Mo. Now, if the item isn't in the list, what it's going to do is it would run through the list until it had finished all of the items, and then it would realize this, and then it would output item not in list. This is the wording of it, so in case they ask you, could you write a description of how a binary search works? That's the one that I took off a mark scheme when I was marking some papers. So that's a word for word exactly what they're looking for. So again, flashcard, go for that one. Again, this is the code. I've included the code on each of them. Yeah, I reckon they could possibly ask you to code that, because it's not as long as, say, a quick sort or a merge sort. So merge sort, quick sort, they could. I mean, it could still be a fill in the gap, and it's not. So if you know how to code it, that's going to help, isn't it? But a binary search, I think, is going to be a good example. Just a flashcard and make sure that you know it off by heart. Linear search. Now, very important that you say it in this particular way. It starts with the very first item in the very first item in the list, compares it to what you're looking for. If it is the item, it stops the search. If it isn't, it moves on to the next item and repeats the process until it goes through the whole list and then outputs item not in list. The big difference with this one is that it can work on lists which are not sorted. So binary searches have to be sorted. Linear searches do not have to be sorted. That is the code for a linear search there, and it just, as you can see, it's just going to go through and just check each of those there. So for I think there's a little bit of pseudocode in there. So if we'll do for I in range length numbers, there you go. So that will be 0 to there. Just tweak this one ever so slightly for you. So yeah, need the -1 there. Okay, and then the brackets, because that was partly pseudocode there, and it shouldn't have been like that. So yeah, you've got the code there. Just, I would remember this off by heart. It's quite a small one. They might ask you at the start of the paper just to write the linear search code. So yeah, you've got that one down as well. The big thing, if the follow-on question might be a 1 or 2 marker, which is just compare the searches. Why would you use one over the other, for argument's sake? Binary search has to be ordered, and very large lists, you're going to use binary search every time. The way that you work out how many searches it's going to take with a binary search is it's 2 to the power the number of searches plus 1. So what that means is let's say I've got 16 items in my list. What do I 2 to the power of to get that number? Well, I do 2 to the power 4, which gives me 16. And then I add 1 to it. So it would take a maximum of 5 searches. It could obviously get it before that, but you want to know what the maximum search is, so it's going to be 5. If it was in between, right? So let's say I had 24 in there. Well, you go for the 1 up. So 32 is the next available one. So it's 2 to the power 5 plus 1. So it'd be 6. So if it's in between 2, because it's not always going to be exactly something 2 to the power that one. So that's how you work that one out. Linear search would be used if it's unordered. And generally, if the list is a bit smaller, sometimes it just makes sense to do a linear search rather than go through and sort it and do all that stuff. Now, going back onto the sort, so we did quick sorts. Remember, the reason I did quick sort is because I think that's the most challenging one, and I wanted your brain nice and fresh for that one. So let's have a look at the different ones in here. So we've got bubble sort. Start with the leftmost item, compare the item with the one next to it. If the one next to it is less, swap the items, repeat for all other items. At the end of one pass through the list, the largest item is at the end of the list. Repeat the process until the items are sorted. So again, flashcard for that. You need your description. Generally, the way I would structure my revision is description. Make sure you've got your description, the code, and being able to do it on an example. Yeah, that if you can do those 3 things on every single sort and search, have all of those 3 things, and you've got it off by heart, they can't ask you anything that you're not going to know. Yeah, so that would be my recommendation. Let's have a quick look at how this works then. So bubble sort generally is the least efficient algorithm to sort. You start with 9 and 5 and you go, is 9 bigger than 5? And it is, so you swap them over. And you go, is 9 bigger than 4? Yes. And then you go, is 9 bigger than 15? No. Now, mistake that people make is they think they go back to the start, but you actually take the 15 on. And you go, is 15 bigger than 3? Yep. 15 bigger than 8? Yep. 15 bigger than 11? Yep. 15 bigger than 2? And then you've got 15 sorted at the end there after a first. And that's what's called a pass, when you have the next biggest item sorted. And then after the second pass, next biggest item is sorted. And you can see there's a lot of sorting going on in this one. It can take a very, very long time to sort. So I think it's unlikely that they would ask you to do a complete sort on quite a large list, because it's going to take you a very long time. But what they might ask you to do is, after, what does the list look like after two passes or three passes, and they want you to know that there should be, after two passes, the two biggest items should be sorted, and how the rest of the list would look in that case. This is the code for a bubble sort. I have seen an example where they've done fill in the gaps and also actually coding it as well, which I actually think is quite hard, because there's a lot of coding in this. So again, flashcard, make sure you practice it lots and lots and lots, just going through it, remember it off by heart. Insertion sort. So insertion sort is like sorting a deck of cards. So essentially you just go through it and you just sort it one at a time. You have an unsorted list, and then you have a sorted list, and you put the item in there, which is in its position, and then you just keep sorting it. So this is what would happen. So 9 is now sorted. 5, we put that into the correct position. 4, we put that into the correct position, and you just go through and do it like that. Okay. That is the algorithm for insertion sort. So again, flashcard, going through that one. I've actually changed my mind on merge sort in the way that I used to teach this, just because I've noticed that the exam board has actually changed the way that they mark this in their internal wisdom. So I'll tell you how to get the full marks on this one. So the description of this is: divide the unsorted list in two. Keep dividing it until one item is in each list. So you keep splitting it up until it's individualized each item. Merge the items into pairs, sorting at the same time. Then merge the pairs into fours. That should say fours there, sorry. Fours. Keep doing this until the list is completely merged. So let's have a look at how that looks. So this is the splitting up part. So split into fours, split into pairs, split into individuals. So that's kind of part one. And then part two is taking the individual items and pairing them up, and then putting them into fours and putting them into eights. Now, a thing which is what I've seen a couple of students trip up on, is when they're putting them back together, what they do is they kind of put them back together, and then what they'll do is then they'll sort them. And the process happens in a single motion. So if we take 11 and 2 as an example here, when I put those back together, what happens is they get sorted at the same time. Yeah, so 11 and 2 sorted. So it's not a two-step process, it's done in one. And you're probably thinking to yourself, that seems a really weird thing to get hung up on. I know, but it's just, that's how the process works. So just make sure that you do that. And I remember people were dropping marks on that one, because it's done in one process. And then, as you can see, when they're put together, they're sorted at the same time. Now, this is the merge sort code. Again, flashcard. I saw a fill in the blank question on this one, which is, being able to understand the code. So again, just practice this on there. Okay. And okay, so we don't need any of that. And okay, great. So the comparison of the sorts. So generally on this one, what kind of question would they ask you? So it's going to be simply, they could just ask you what kind of what kind of going to be the time complexity, and I would go with the average. Yeah, so just go with the average on these ones. You could, and it's just about talking. It may say best case scenario, so have that one down as well. So the best time complexity, and you've got those ones on there. They also sometimes have an evaluation question where they would say like, which one would you recommend and why out of all of the different sorts, and you need to talk about each of them, and you can obviously use time complexity as a way of justifying your reason for using something. So, if you had to compare the difference between a merge sort and a quick sort, you could obviously say that over bigger lists, it's actually worse to use a quick sort. And I just thought I'd include that little example up there where it says merge sort is much better for it's much better for actually for larger lists. So quicksort is more efficient and works faster than merge sort in case of small arrays. So quicksort, smaller list, you would use that. Merge sort, much larger lists, you use that. So that's a really good evaluative point, and that's just for the big sort of 9 to 12 markers that you might potentially get. And then you can use the time complexity of this. So generally, bubble sort is really, really slow, and you can use the time complexity there to justify that. Insertion sort is slightly faster, but still similar time complexity, but you can use this and talk about this one. Merge sort and quick sort, whilst they have the same time complexities, you can say, yeah, they do, but that quick sorts are actually better for shorter lists. Merge sorts are quicker for larger lists, and you can talk about that. And then if you're bringing up the big O notation for it, that's just going to help make your case in those slightly longer style questions on there. I just included the ones on linear search and binary searches. But yeah, you've got some good talking points there that you can go through. So that's all of the searches and sorts. I hope that was useful, people. And if you've got your test coming up, best of luck. Hope you do really, really well.